Okay, please go ahead now.
Yeah, okay. Thank you for the introduction. I'm very happy to share my research in this lecture. And my research goal is to develop generalized policies for robots to navigate and interact with real-world environments. So in the following slides, I'm going to talk about what is robot navigation. And then I will talk about our previous work in indoor navigation, outdoor navigation, and also scene understanding. Please feel free to ask any questions during the presentation, and don't hesitate to interrupt if something needs to get clarified as we go along. So what is robot navigation? Robot navigation is very fundamental task in robotics that involves enabling a robot to reach specific goals reliably and efficiently. There are multiple applications in both indoor and outdoor scenarios. For outdoor applications, robot navigation can be used to handle tasks such as last mile delivery, as shown in the first figure, and also surveillance, serve as lawn mowers, or be used in agriculture. And for indoor applications, robot navigation is also widely used for warehouse management, as shown in the second figure, and also the house cleaning tasks. This video shows how robot navigation is used in the last mile delivery task.
Jing, sorry to interrupt. Just one quick thing. So I'm not sure if your like the videos you show in your slides has an audio. Yeah, I think when you share your screen, you need to click on that option, right? Also share the audio.
Okay, let me check. Computer audio, video phone. Oh, sorry.
Yeah, no worries. You can share your screen again.
Can you hear this? Can you hear the voice, the sound?
No, actually, I couldn't hear
Uh,
anything except your voice.
let me
So
check
there
how
should be
to.
a button like when you click the share, then typically that is at the bottom left.
Oh, I saw this one.
Yes, that should be the right one.
What can mount a curb, has
Does
6
it work
wheels,
now?
and is
Yeah.
bringing a fresh burrito to your door? A food delivery robot, of course.
I'm sorry, does it work now?
Inside this Starship bot is a meal
Yes,
ordered
it
through
works.
DoorDash. It's coming
Great.
soon to a sidewalk near you, as long as that sidewalk's in Redwood City, California. When you place an order, the robot springs to life and navigates to the restaurant. An employee puts the food inside and closes the hatch, sending it on its way. At the other end, you get a text message with a link saying your order's being delivered, and when the robot arrives, you unlock the hatch with a button on screen. Each Starship bot has 9 cameras and ultrasonic sensors for obstacle detection. They can travel as fast as 10 miles an hour, but are limited to 4 miles an hour for now. There's even a special mode that lets the robot cross the road safely. Human handlers will keep an eye on the bots during deliveries in this pilot phase, but the idea is they'll be almost fully autonomous in the future. I followed the bot around on a delivery run, and passers-by thought it was pretty cute. But what if someone tries to steal your meal? The robots only weigh 40 pounds, so if you're really hungry or strong, you could try and swipe it from the curb.
What we've built in are kind of variety of anti-theft preventions. For example, we have cameras, we have GPS tracking, we have two-way audio, alarms. So if there's any tampering with the robot, theft attempts, the robot will immediately notify a human operator who can take control of the robot, speak to the vandal, or request police assistance.
Yeah, this is a example of the application in outdoor scenarios. And we are going to show a demo, a video for indoor use cases. The video shows for indoor and entertainment applications and
A
also
robot.
the house surveillance
What are we gonna do
applications.
with a robot?
Amazon created
Well,
this
Astro,
product called Astro to
follow
do
me.
these tasks.
Hi, Grandma. I miss you.
I miss you too. Hey, you got the toy I sent.
Yeah, I love it. Astro, follow me.
Cool. All right, race ya.
Come on.
Told you I turned it off.
And now I totally believe you. Ooh, yikes.
Message from Steve. Remember to eat something green today, Dad.
Check.
Hey, Barbie. Just return the dogs.
Astro, let's dance.
Thought we weren't home, huh? You thought wrong. It's a good try, though.
What? Thank you. All right, I'm in.
Knew it.
All right. So those are the demos for the indoor and outdoor experiments. And so navigation generally includes three subproblems, which is mapping, localization, and planning. Mapping builds a spatial model of a robot's environment, and localization determines where a robot is with respect to the environment. And planning is to move the robots in different scenarios. And the intersections of the subproblems also come up with new tasks. For example, the intersection of mapping and localization is SLAM, which is simultaneous localization and mapping. It does mapping and localization at the same time. And the intersection of localization and planning is active localization, which requires the robot to navigate to the best place to get more signal or environmental information for accurate localizations. And the intersection of planning and mapping is exploration, and it requires the robots to find the best trajectory to explore more information of the environment. And my research is mostly in planning, including action generation, trajectory generation, and scene understanding. So for indoor navigation, I mostly worked on the collision avoidance and place recognition problems. And for the place recognition problem, we mostly address two challenges. The first challenge is the collision avoidance with occluded dynamic obstacles. As shown in the left figure, in this scenario, people could suddenly appear in the vision of the robot. So the robot has to agilely interact with the people. And the second challenge is the navigation in dense crowds. In the second figure, in this scenario, the robot needs to find any open space in the crowd and squeeze in and move towards the target. And this is a representative work we did for robots moving in dense crowds. This approach is purely trained in simulator, and we use on-policy reinforcement learning, PPO, to train this policy. And for the input of the model, we have 2D LiDAR, RGBD image, relative goal position, and robot's velocities. Especially for the prediction model, we segment the pedestrians in the robot's vision and predict the positions of the pedestrians in the next time step. And then we use convolutional layers to process the predicted information and the background information of the image. The reward function is designed to achieve collision avoidance and also to encourage the robot to the target. The reward function includes 4 parts. RG here is to encourage robots to move towards the target. So it will provide a reward when the robot goes closer to the target. And RC and RSafe dist are the penalties to let the robot to avoid collision and also keep away from the obstacles. And ROSC here is to prevent oscillation. The oscillation is like this. So without this term, the robot will wag a lot and run a zigzag trajectory. And these simulation environments are used for the training. The simulation environments include many robots and many people and also different shapes of floor plans. And to make the training easier, we train the model in the environments with increasing difficulties. And to alleviate the reality gap, the model prediction, we use a model to we model the pedestrians' social velocities in the gazebo simulator and design complex environments for training. So the left environment is a corridor with dynamic pedestrians. And in this scenario, the robots are trained to find clearance and avoid pedestrians in the corridor environment. And the middle scenario has occlusion. And in the scenario, the robot learns to pay attention to the corners and also the occluded areas for collision avoidance. And the third scenario is a dense crowd. When the robots learn how when the robots finish learning like how to avoid the regular obstacles and how to go to the target, in this scenario, robots need to find any open space to squeeze in and to achieve the target in a very highly dynamic crowd. And to increase the training speed for each scenario, we parallelly train multiple robots at the same time. So some takeaway from this project. In this project, we noticed that LiDAR sensor with very accurate geometric information can help robots to behave more agile to find the narrow open space in dense crowds. And the RGBD sensor with very rich context features can provide more information about the environment and help robots to move smoother when the robot interacts with people in front. This video shows the experiments of the trained model for collision avoidance in different scenarios. The first scenario is L and T junctions, and the people can suddenly appear in the vision of the robot, so the robot needs to actually interact with people. And this scenario has very dynamic objects, and people are walking around, and the robot needs to predict the human actions and avoid colliding with them. And this scenario has very dense crowd. And in this scenario, the robot needs to find the open spaces to squeeze in and move towards the target. Okay, the motion planning requires the waypoints for the robot to follow. So for map-based indoor navigation, the robot still needs to know where it is. So for this problem, we used place recognition method to handle this task. And when the robot gets, in this task, we use RGBD observation. And for the place recognition task, it matches the observed point cloud, RGBD point cloud, with the stored database and find out the most similar view. And then the robot knows where it is. The place recognition in indoor scenarios is quite challenging. There could be repetitive features that can confuse the matching, or there could be not enough features to use for place recognition, especially when the robot is very close to some large objects. So to handle those challenges, our intuition is to use multiple modalities and also multiple stages for the place recognition task. The first approach is called POCO. The model encodes each RGBD observation into a global descriptor and compares the similarities between the descriptors of the query observation, which is observed in real time by the robot, and the database to find the robot's position. In POCO, we encode the geometric and also color information by the feature extractor. And in the feature extractor, we use multiple layers of reducers and clusters to encode the RGBD point cloud into a vector. And the reducer, as shown on the left figure, on the left bottom figure, the reducer is to reduce the dimension of the features by aggregating a large number of points into a smaller number of points. And the cluster, as shown in the right bottom figure, is to process the multi-scale features by the aggregation and the dispatching mechanism. So in each cluster, after aggregation, we get higher level sparse center features, and then the dispatching correlates two scales of center and point features, and use the center features to enhance the point features. But POCO cannot provide very accurate place recognition by only using the global descriptors. So in CSAPR, we use the second stage to rank the candidates. The first stage is based on POCO, and the second stage compares the local features of the two RGBD point cloud. It contains two models. One is the self-context cluster, and it is to process the local features of a single frame. And the second is a cross-sourced context cluster, and it is to process the similarity of the local features in two RGBD frames. So from the left side table, we can see that the two-stage model dramatically increases the accuracy of the place recognition and improves the recall at one from 64 to 84. And from the right side table, we can see that the re-ranking model is also very efficient, and it has the least inference time compared with other state-of-the-art methods. And this video shows the real-time experiment of our place recognition methods. We can see that the recall at one and the recall at two sometimes the images jumps a lot. So in real world usages, from experience, we evaluate those record 1 and record 2 and to decide where the robot is. All right. But for indoor navigation, there are still unsolved problems. The first problem is that for indoor scenarios, they typically have very flat floors. So we didn't consider stability and traceability issues when the robots are running on varied terrains, for example, in outdoor scenarios. And the second problem is that these approaches are only trained in simulators with very simple geometric information. But real-world scenarios have more complex situations, especially the outdoor environments with unstructured vegetations. So given those issues, I moved the robot outside for outdoor motion planning in off-road terrains. And for outdoor motion planning, besides collision avoidance, I mainly addressed navigation in 3 other challenging scenarios. The first scenario is the terrain with different gradients. So when the robot is climbing a hill, we don't want it to flip over on steep gradients. And the second scenario is when the robot is traversing woods or tall grass. In this scenario, it has lots of occlusions, and in the scenario, robots should be able to traverse the grass, the pliable grass, instead of treating them as obstacles. And the third scenario is the bumpy terrain for wheeled robots. So when the robot is running on very bumpy terrain, it should not move too fast and damage its structure. This is a representative work of outdoor motion planning in off-road terrains. And this is also the motion planning part of our map-based navigation pipeline. And in this approach, we use curriculum learning with multiple stages to train the model with various terrains. So in each stage, only the functional models are trained for a specific terrain, and other models are fixed. So for example, when the robots are training on the terrain with different elevation changes, we only train the elevation map model and the policy model. And in the final stage, we fine-tune the perception models in a highly realistic simulator using the Unity engine to reduce the reality gap. This table shows that we achieve safe and stable motions in these complex outdoor scenarios. And specifically in uneven terrain, we have least vibration and drift. And in the scenarios with static obstacles, our approach has comparable success rate with other approaches. And in the scenarios with different gradients, our approach also have least elevation changes. This video shows the experiments in the real-world scenarios. In this scenario, we can see our robot runs slow in bumpy terrain and fast on the flat terrain. So we have the least vibration. And this scenario has slippery terrain with fallen leaves and grass. The blue trajectories are the actual trajectories, and orange trajectories are calculated by the robot's odometer. So we can see our approach has least drift in the slippery terrain. And in this scenario, the robot has to go to the top of the hill. And we can see that our approach drives the robot through the areas with the lowest elevation gradients. And this scenario shows that our approach can avoid high gradients and also the non-traversable areas. This is another example of climbing hills. So the target is on the top of the hill. Okay, so for the challenges of running robots in tall grass and different lighting conditions, we designed the approach GRASP to address the challenges. Because LiDAR and camera have very different modalities of information, so we use them under different conditions. For example, if at night, RGB images cannot capture much useful information, so the LiDAR plays more important role in the navigation. But if the robot is traverse tall grass, LiDAR input could be very noisy, but camera can provide some semantic information and run the robot to traverse the pliable grass. So in this project, we trained the model to learn the reliabilities of these two sensors and put more weights to the most reliable sensor during the navigation. This video shows the performance of GRASP in different off-road scenarios. So we can see that our approach can detect both pliable and non-pliable vegetations for navigation. So this part is pliable vegetation, pliable grass. And this part is more about non-pliable, the bushes and trees. This is also an example of pliable grass. And also during night, this approach can also balance the reliabilities of camera and LiDAR to navigate in low lighting conditions. Okay, so for this outdoor map-based navigation approaches, there are still unsolved problems. So the first problem is that these approaches are mostly motion planning approaches using the map-based navigation. So for long-range navigation, the sub-goal choosing highly relies on the accuracy of the stored map. So it makes it inflexible to the environmental changes, such as weather variations and constructions. The second problem is that the motion planning approaches also rely on efficient and accurate path planning methods to generate good waypoints. So from Route 2023, I moved to outdoor global navigation. The problem I worked on is the navigation in a semi-mapless environment with topological maps or GPS. And I mostly worked on two challenges. The first challenge is to choose the best direction to move the robot. So for example, as shown in the left figure, if the goal is behind the building, should the robot follow the main road or go to the right side? This is not purely an optimization problem, but more about the human intuition. For example, if the target is really far, we don't know, and we also don't know the exact path to the target, we might want to walk on the main road first. And then when the target is very close to the robot, we can go to the narrow roads. The second challenge is the traversability analysis. So during navigation, robots should know where they can traverse. And for different types of robots, the traversabilities could be very different. For example, the legged robots can go on stairs, but wheeled robots cannot. And this is a representative work for traversability analysis. We address this problem from the navigation perspective. So in this work, instead of estimating the traversability of the scenario, we generate diverse trajectories to cover all traversable areas in front of the robot. And in this approach, we use CVAE-based generator to generate diverse trajectories by linearly transforming the embedding vector into diverse embeddings. And because the embedding vectors in the CVAE formulation represent Gaussian distributions. So we can naturally use the variances of the Gaussians as confidences of the generated trajectories. The input of this model includes 3D LiDAR point cloud and historic robots' velocities. And in the middle, H psi is a linear transformation to linearly transform the embedding vector into diverse embeddings. And for the decoder on the right side, each decoder generates one trajectory. And to make the generated trajectories different from each other, we use attention model to provide the information of other trajectories and make it as a condition to the decoder. These are the loss functions of MTG. So for CVE lower bound, in the reconstruction loss, we use Hausdorff distance to calculate the distance between the generated trajectories and the ground truth trajectories. And because we generate a fixed number of trajectories, there could be more or less traceable areas compared with the number of the generated trajectories. So we might have some redundant trajectories in this case. And to make the training converges faster and easier, and for each ground truth trajectory, we only choose the closest generated trajectory to calculate the loss. So which means that we don't care about if the trajectory number is larger than generated trajectory number is larger than the actual traceabilities of the environment. And in the diversity loss function, tau O represents redundant trajectories, and the tau C are regular trajectories. So if there are redundant trajectories, we make them close to their nearest ground truth trajectory, and for regular trajectories, they should be distant from each other to be diverse and to cover the entire scenario. And here we also use Hausdorff distance to measure the distance among all those regular trajectories. And the third loss function is the traceability loss function. And we apply this loss function to all the trajectories and prevent them lying on non-traceable areas. This is a video demonstration of MTG. And in the video, the darker color of the trajectories means the lower confidence, and the lighter color means higher confidence. And the top right figure shows the selected trajectory, which is not the least confident and closest to the target. And the top right figure shows the third-person view of the navigation. And we use a dynamic window approach as motion planner to follow the generated trajectories for collision avoidance. As we can see that the generated trajectories cover the traceable areas. And later, you can see a person going in the vision. So these trajectories can also ignore the dynamic pedestrians.
Just a very quick question. So I can see in this video, I can see like there are right trajectories and black trajectories. Maybe I missed something, but could you explain like the difference or
Right.
the color? What does the color mean here?
Right. So we have the confidences of the generated trajectories, and those confidences are from the variances of the Gaussian embeddings. So in the middle here, so we have this embedding Z, right? So this Z could be, those could be the Gaussian embeddings. So each Gaussian, so for each trajectory, we have different waypoints, and those waypoints have different, the Gaussian distributions. And we use the variances to represent the confidence of the trajectory. So the darker color in this video shows lower confidence, and the
Oh,
lighter color means higher confidence.
I see, I see, I see. Got it. Thank you.
Yeah, but in this case, sometimes we can also see that those trajectories, for example, this part, the left side, the trajectories also lie on this the grass and also go across the curbs. But this is some out of distribution scenarios, and there could be, because the data set is not in this data set didn't cover the scenarios like this.
Another quick question. So for
Sure.
these out of distribution scenarios, like does your method have any specific techniques to mitigate the OD issue, or you just um, test this model like but during testing there could be some OD issues.
Yeah, during testing, there could be some issues.
I
So our
see.
data set actually, so we use we separate the data set for testing and training, and the testing data set actually covers some areas like this. So the curves are really low. So it's very different from the training data set. So that's why those areas is not sure. The model cannot really cover those distributions. And
I
you can
see.
see the trajectories like on the grass, and they go across the curves. But we can also see that those trajectories have really low confidence. So this is also another advantage, that using the confidence to measure the trajectories.
Yes. And what is the horizon? So you are planning some kind of long horizon trajectory for future, right? So
Yeah, we
what's the
estimate.
horizon?
Yeah, we estimate 15 meters.
Oh, 15 meters.
Right.
I see. Got it. Okay, thanks.
Yeah. So to solve the generalizability issue, which is an out of distribution issue, given all the trajectories from MTG, in TGS, we use vision language model to select trajectories. So first, we transform k consecutive frames of trajectories into the current frame and select representative trajectories by Hausdorff distances. And then we project the trajectories from the robot frame to the image plane. And the selected representative trajectories, the gray color trajectories show in the right side figure. And we label the trajectories using a sequence of numbers in the image. And then we use ChatGPT 4.0 to select one trajectory to follow. So on the left-hand side, the prompt shows that we want to select the trajectory similar as what a human does. And we also apply constraints such as the robot should walk on the pavement and avoid bumpy terrains and follow the rules of traffic. And for wheeled robot, we also add the constraints that it cannot go over the curbs. So the selected trajectory is marked as a red color, as shown in the right side figure. This is a result of TGS, and the second row shows the trajectory selected by TGS using red color, and all other MTG-generated trajectories are in gray color. And we can see that it handles the navigation very well in most of the scenarios, and especially to detect the traceabilities and also the crosswalks. And to further evaluate the capability of VLMs in traceability analysis in Behave, we use VLMs to segment traceable areas in the input image and use large language models to provide actions to the given target. So this video shows the performance of our approach in different scenarios. As we can see that our approach generates a behavior cost map that reflects both the likelihood of the behavior objects and the desirability of associated actions in the language instruction. So for example, we can detect stop hand gesture and also the stop sign, which is shown in the green circle. And then we correlate the behavior object with robot stop action. So the robot can stop there. And we can also detect crosswalk and then correlate the crosswalk with robot's follow action. This clip shows how we detect the crosswalk and correlates to the follow action. This clip shows that the robot can also detect the stop sign and stop in front of it. And we also did some experiments in off-road terrains. So we can also correlate the water puddle and the grass region to avoid the action.
Just a quick question. So my understanding is that in this framework you employ the VLM, right?
Yeah.
So did you deploy VRM on board or?
Yeah, it's actually really slow. So sometimes it takes like 10 seconds to provide some waypoints. So
I
yeah,
see.
so in this model, we directly provide the target, the estimated goal. So that's why and the local planner is also DWA. So basically, the VLM and LLMs are only to provide like some waypoints.
I see. I see.
But the
And
cost map is in real time, because
yeah, yes.
the clip stack is really fast.
Yeah. So did you use a laptop to run this language model and the vision language model?
Yeah, so we have I'm not sure if you can see the robot.
Mm-hmm.
Oh yeah, here. So we have the laptop is actually building. Actually, we have the CPU in the robot, building in the robot, and so
Okay.
maybe get a closer look. Oh yeah, this one. Can you see this robot? So actually,
Yes.
we have
Yes.
something. Yeah, we have some computational resources in the robot, and we also carry a card. We have the Wi-Fi and Wi-Fi router and everything there. So
I
yeah,
see.
this
I
is
see.
basically the setup.
Okay. Okay.
Mhm.
So since but because I suppose like you have like generally speaking you have a branch with higher frequency and a branch with lower frequency which contains the foundation models, right?
Exactly. So
So
mhm.
yeah, and my question is for this uh lower speed branch, uh is everything right now acceptable, or you still think there is a urgent need to improve the efficiency or like make this slower branch faster?
Yeah, I think this is a very critical problem. So the speed is definitely needs to get updated and get faster. And but another very critical problem is that
Mm-hmm.
the model, for example, the language models, here we use ChatGPT 4.0
Mm-hmm.
for large language model, but it's not really stable. So
Yeah.
sometimes, we need to do some prompt engineering, and when the version get updated, we need to design new prompts So it takes lots of time, and this
Yes.
should also be get updated.
Yeah, and because you are using the OpenAI API for GPT-4o, I guess.
Yeah.
So that means you like generally like the system or the whole system needs to have access to internet.
Yeah, exactly. This is
I see.
another issue. So we need to
Oh,
keep the Wi-Fi router very close to the robot.
oh,
So
I
in the
see.
video, we didn't see the card, right, and Wi-Fi router, but in real world experiment, we need to carry it behind the robot.
Oh, I see. I see.
Yeah.
I see. Did you ever try to use some open source model like a VRM, so you don't have to use uh, API or you don't have to like access internet?
Yeah, we use clip sag. Is it also, VLM, sort of VLM?
Mm-hmm.
But yeah, we didn't use other methods because for this project, the task is to segment the image. So that's
Oh,
why we
okay.
use this one. Yeah.
I see. I see. Got it. Okay. Yeah. That's all my question. Thanks.
Mhm. Yeah. So as what we discussed, the ChatGPT is not stable and takes too much time in trajectory selection. So in DTG, we use diffusion models to imitate the human-like trajectories. The perception encoder is the same as MTG. And for the diffusion process, we design a novel conditional RN model because previously the original UNet or transformers, they are too slow for multiple stage diffusion process. And in the model processes time steps with a cosine positional encoding. And then we use multiple GRU models to process the trajectory features. And to make the trajectory smoother, here X is not the positions of the waypoint, but the positional differences of consecutive waypoints. So they are delta positions. And in the last time step, in the last step of the model, we accumulate the delta positions to get the trajectory. And this is the result of DTG compared with other approaches. And from the experiment, we can see that DTG is also capable of estimating the geometric shapes of the buildings. For example, in the first column, we can generate the trajectory in the occlusion, but other methods cannot really do this job. But these approaches still have some issues. The first issue is that the training heavily depends on the available data sets, but there are a few open source data sets for especially long range navigation. And the second problem is that the model lacks the interpretability, making it very difficult to assess whether it fully understands the traceability of the scenarios. So for the dataset issue, we propose a new global navigation dataset with 5 traceabilities. We covered 10 campuses around the DC area, including 668 minutes raw specs with 350 buildings. And we also open sourced the data processing pipeline to encourage other users' contribution. And in the dataset, we have 3D LiDAR, RGB camera, 360 camera, GPS, MU, and odometer data. So the right-hand side shows a sample of the GMU campus. We also did some map-based global navigation experiments with the traceability map to evaluate its accuracy. And for the path planning, we use RT star to generate trajectories given the GPS start and go positions in the traceability map. Yeah, as what we can see that for different types of robots, they can run on very different traceabilities. And for the legged robot, they can also go off the curbs or the off-road terrains to avoid collision. And for the issue of traceability analysis, we did a project called ET-Former. This project is to understand the environment and create a voxel model to capture the semantic information of the scenario. And this task is also called semantic scene completion. ET-Former takes a monocular RGB input to estimate the semantic occupancy map and complete the scenario. And it also estimates the uncertainty of the predictions. In this project, we use two-stage pipeline for the semantic scene completion. The first stage is to estimate the occupancy map. And the occupancy map will be treated as a query input to the second stage. And the second stage estimates the semantic map and the uncertainty map. Because the two stages use the same deformable triplet model, we talk about the second stage first. In the second stage, we use the conditional masked autoencoder for scene completion because the same as what we did in MTG, because the embedding space is also the Gaussian space. So we can literally use the variance of the Gaussian as the uncertainty of the estimation. And here, each Gaussian distribution represents a voxel. So we have the uncertainty of the voxels. The input image and the occupancy map from the first stage will be processed by the cross-deformable attention model to generate the CMAE Gaussian embedding vectors. And then the variances of the Gaussians can directly build an uncertainty map. And we also propose a novel triplet-based deformable attention mechanism as a decoder to generate the semantic occupancy map. In the triplet-based model, we used the voxel's positional encodings as ways to project the voxel features into the three orthogonal planes. And then we design an efficient deformable attention mechanism to process the features. And finally, we can aggregate the features to the 3D space for semantic estimation. And about the novel deformable attention approach, we have two major innovations. The first one is that compared with original deformable attention, our reference points are way less than the query points. However, to make the reference points representative enough in this situation, we sample the reference points which can cover all sort of feature spaces. And in this project, the reference points should cover most areas of the image and also the 3D voxel space. The second innovation is that instead of using one reference point feature to enhance one query point feature, we use the global information of the image to enhance each local query feature. This task is achieved by the multi-head attention mechanism. And this is the architecture of the first stage. And in this stage, we use DNOV2 to get the depth image and project the depth pixels into the voxel space, and then to calculate the occupancy map. So here, the deformable triplet is the same as the one we used in the second stage. This table shows our result, and we can see that we have much better IOU and MIOU. And the benefit of the triplet-based deformable attention model is that we can detect very big objects more accurately than other SOTA approaches. So for example, we have higher values in MIOU for the roads and cars and buildings and some large areas of vegetations. This video shows the result of the semantic map generation compared with other SOTA approaches, and it also shows the uncertainty map at the later part of this video. So this is a sequence of KD dataset, and we can see that monoscene and voxformer cannot accurately predict the semantic objects. And also for Vox Former, it has very noisy estimations in the out of view areas of the camera. And this clip shows the uncertainty map with the semantic map. So we can see that the red color represents very high uncertainty, and the blue color means the very high certainty. So the uncertainties mostly happen in the occlusion of the robot's vision and also the out of view areas of the camera's perception. Yeah, that's all my previous works. Thank you for listening. Do you have any questions?
Oh, yeah. Thank you so much for the very nice talk. Yeah, and actually it goes through a lot of your recent research. Yeah. Yeah, thank you so much for giving us this presentation. From the audience, is there any questions?
I had a small question.
Oh, you go ahead. You go
You
first.
first. Oh, okay. I have a very small question about the first stage of your ET former.
First stage,
It mentions that it utilizes a Dino V version 2 to get the depth estimation.
Uh-huh.
In my knowledge, the Dino V2 provides some self-supervision feature for the image perception. So how do you estimate the depth for your monocular observation?
So we